Hello everyone, my name is Perez-Pinero and I want to highlight first my collaborators, a master student Changhun Jeong and Professor Sigurd Skogstad. So we are interested in looking at problems of managing energy storage systems. The thing with these problems is that we have to deal with a lot of uncertainty. So some sources of uncertainty are renewables that comes into the picture, solar and wind. Also waste heat in case of thermal systems. We have to manage these resources in the face of stochastic spot electricity prices. These are very spiky, uncertain demands, forecasts for temperatures and loads that are not very reliable. So we have to design policies to perform well under all of this variability and uncertainty. So we look at a case study here that is a district heating network. And the sketch of the problem is here in the poster. So these are the elements in our problem. We have a waste incineration plant that is producing energy. We have a demand here, which is the households connected to the district heating network. We have a grid, so we can actually use maybe electric boilers to satisfy the thermal demand. And we have also a storage device, which in reality is a hot water tank. So at every point in time, we can manage this system in different ways. So we have actually to decide the energy flows between these elements at every point in time in such a way that we minimize the cost paid for the electricity over time. So there is a lot of ways to solve this problem. In this particular work, what we did was to design a very simple parametric control policy, where the philosophy is the following. We want to use the waste incineration plant first as much as possible to satisfy the demand. And if we have surplus of energy, we want to store it. So that idea is taken here in this policy. And the second idea is, okay, we want to identify opportunities when the price of the electricity is low, is cheap, so we want to store that electricity to use it later when maybe electricity prices are high. So we want to charge when prices are low and discharge the battery when prices are high. And we also want to satisfy the demand at every time. So if at some time the combination of waste heat and storage is not enough to supply demand, we purchase the remaining part of the electricity from the grid at the current price. So this policy is parameterized in terms of these two parameters on two bounds on the prices. And what we did was to tune these two parameters with some stochastic models, which in reality may be drawn from historical data, to tune this policy to give good performance. So after tuning this very simple policy that in reality can be implemented with just selectors and PID controllers, for instance, we compare this with different formulations on MPC, in particular 3, certainty equivalence MPC. What it does is certainty equivalence means that we substitute random variables by their average values. Parametric modified MPC, basically here we are solving a myopic optimization problem, but we put there some tuning parameters and we tune that to be robust under uncertainty. And then multi-stage scenario tree MPC, which basically constructs a scenario tree of the future and optimizes the average cost, taking that scenario tree into account. So we see here that our parametric policy performs really, really well. And basically the takeaway with this work is that in some cases we can exploit the structure of the problem to come up with parametric policies, maybe as a function here of two parameters, which if they are well tuned, they are very, very effective. So sometimes we can get away with simplicity if we know how to take advantage of the structure in our problem. Okay, thank you very much.